All right, so we're going to continue working with integrals, but we're going to talk about net change, right? And so let's think about what net change is. So suppose you had, a liter of a liquid, right? And so that's what you started with. You start with a liter of a liquid, and then so suppose to that liter, you keep adding, 5 milliliters per second, okay? 5 milliliters per second. After 10 seconds, how much have you added? So if you're 50. Yeah, 50 milliliters, right? And so how much did we start with? One. And so now we have the liter plus the 50 milliliters, right? 1,050 milliliters. So do you see, what did you do there? You did it so quickly, you don't even know. In your mind, you calculated how much new stuff was added, and you did that basically like by adding up all the stuff that was added, right? 10 times, right? This many per second, 10 seconds. Isn't that like an integral, right? Adding up, right? Infinite numbers of things. So first you added up how much new stuff was added, and then you combined it with how much you already had in order to come up with the final amount, okay? That's the sort of thing that we're going to do, okay? The classic example is with distance traveled, but then, there is also so many other examples of what we call net change. Net change is how much, something is changing by. Okay, so let's start talking about particle motion, right? Remember, and from the very beginning, I've always told you, never forget about this stuff because it's going to show up all the time, and now it's going to show up officially again. Okay, so when we talked about particle motion, what did we talk about? We said if the velocity was positive, something was moving to the right, and we said if the velocity was negative, something was moving to the left, right? Now, we also talked about displacement there as the integral from A to B of v of t dt, right? So remember what displacement was. Initially, we first said that, we first found it as area under a curve, okay? And then we said, oh, wait, that's also the integral. So when you do the integral, okay, what's the integral of velocity? It's position. So s of b minus s of a, right? Think about it, right? This is the antiderivative of velocity, which is position, because if you took a derivative of position, you would get velocity. So what this is the final position minus the initial position. Okay? All right. Now, so what is the final position of something? Right? So suppose something is moving. When it stopped, right? Well, yeah, so it's basically where it started, the initial position, right? Plus the displacement. That will tell you the final position of something, right? So suppose you know that something started at x equals 3, and then you know that it moved like 7 meters, and now you know that it's at x equals 10, right? And then what we also have talked about is that the total distance is the integral of the absolute value. Okay? Questions here? Okay, so I just want to add one more thing about final position. Final position is S of B, right? Okay, now take a look at this line right above it where we have talked about displacement. Take a look at this. Okay? All right, so what did we say below for final position? We said it is the initial position plus how much it moved, the displacement. Well, what's the integral for the displacement? V of t dt. So do you see how conceptually the final position is where it started plus how much it moved? Is the same as if you took this equation in the blue and solved it for final position, you get the same thing, don't you? Because if you move S of A to the left side, then you get S of A plus the integral. So it's the same thing as we did here. Okay. Now, take a look here. The function v of t is the velocity in meters per second of a particle moving along the x-axis. Use analytic methods to do each of the following. Okay. Determine when the particle is moving to the right, to the left, and stopped. Okay. So, this is v of t. So, we want to know when it's moving to the left, to the right, and when it stops. So, let's first set the velocity equal to 0. Okay, so 3t is 24, t is equal to 8. Okay, now the overall interval here is from 0 to 10. So I put this on a number line. It's a closed interval from 0 to 10, and 8 falls about here, right? Now this is positive before and negative after. So we say it's moving to the right. You plug in values into here. So it's moving to the right from 0 to 8. Open at 0 because, you know, it was starting from there. We have no indication to say that it was changing direction there. But open at 8 because the velocity is 0 there, and it's moving to the left from 8 to 10. If the equation was such that, for example, the velocity was 0 also at x equals 0 or t equals 0 or at t equals 10, then that would be an indication of maybe, you know, it might be changing direction there or it stopped there. So you would not include those points. But since there is no indication of that, you include the 0 and the 10. Yeah?
Can the rule apply because it's like an individual x? It's not like x squared, x fourth, or like in this case t squared.
Right. Yep. But like for like x equals 10, it could have been like something else.
Of course.
Right? Yeah. Okay. So part B. Find the particle's displacement for the given interval. Yeah. So displacement. If s of 0 equals 3, what is the particle's final position? Okay, so the displacement is from A, which is 0 to 10, 24 minus 3t dt. Okay? So, what does that give me? If you do it, it's 90 meters. Okay? Okay, so what does that mean? If the displacement is 90 meters, positive 90 meters, it means the particle at the end of the 10 seconds, the particle is 90 meters to the right of where it started. Okay? Now, in the interim, like in the middle, okay, it could have started from someplace. It could be that it moved to the right a little bit, to the left a little bit, then back to the right, then back to the left, and then back to the right, whatever. The point is, at the end of the 10 seconds, it is now 90 meters to the right of where it started. That's what displacement of positive 90 means. This is not total distance. Yeah?
Do we know it's to the right because it's positive?
Right. And the right is the positive direction.
So we're negative 90 meters to the left.
Right. Because it's moving along the x-axis.
Yeah.
Right? So you know that the right is positive. Okay. No, this is the displacement. Only the displacement. It's how much it changed. Now, I see where you're going. The final position, s of 10, is equal to s of 0 plus the integral from 0 to 10, 24 minus 3t dt. This is the final position. Okay, the 90 is just how much it moved over the 10 seconds. All right? So, this, in the problem, we're told it's 3 plus this one is 90, so that's 93 meters. Okay. And for C, to find the total distance, we're going to do the integral of the absolute value of this dt from 0 to 10. Okay, and you can plug it into your calculator, and then you get that this is equal to 102 meters, right? So now,
So that's not something we have to do then.
for C you do.
See, we do have to do it that way?
Oh, by hand, I'm sorry, I didn't. No, you can just plug all these into your calculator. I mean, most of the time you're going to get functions for these that are not that are too complicated to do by hand anyway. And so, you know, you are more than welcome to use the calculator for these.
So this will be on the calculator.
Yeah. Plus, like here, like you're confident, you know, we're confident that you know how to integrate now. Okay. So going back to here then, right, to the very beginning for part A, remember how we had said it started here, and then we said for 8 seconds it moved to the right. Okay, so at t equals 8, it was here, and then it moved to the left a little bit, t equals 2. I'm sorry, until t equals 10 for 2 seconds, right? Okay, the whole distance that it walked or traveled was 102 meters. However, this distance is how much in the blue? 90, just 90, because the displacement was 90. Okay?
It's almost 93.
Now, 93 is this. If you continue this, this is where x is 0 is. At t equals 0, it was here at x equals 3.
Oh,
So 93 is where it is from the origin.
So it started at 90.
Right. No, it started at 3.
Yeah, 3.
Yeah. Okay? So now we know the whole story. Gavi's satisfied. Yeah. Okay. Next. Okay, the function v is the velocity in meters per second. I always like to highlight the units of a particle moving along the x-axis. Use analytic methods for the following. Determine, again, when the particle is moving to the left, right, and stopped. Okay, so let's do that first. So this time, I have 6 sine 3t. Set that equal to 0. So 0 is sine 3t. Okay, now, on the unit circle, sine of x is 0 at 0 and pi. That means when the angle, where did it go? When the angle is equal to 0, or when the angle is equal to pi, okay, that's where sine is equal to 0. Okay? So this is 0 when 3t is equal to 0 or pi, which means t is equal to 0 and pi over 3. And we have to make sure that we've included all of them until pi over 2. Okay? Okay. So now, let's put this on the number line. 0 to pi over 2 is our domain. Pi over 3 falls here. Okay? Now, initially, right? So like right over here, this falls in the first quadrant. Sine is positive. And then this takes us into the second quadrant. Sine is negative. Okay? Okay.
Because pi over 2 is that.
Right, but whatever this is, you have to plug it into the 3t.
Oh, so you're multiplying.
So you're multiplying it, yeah. Okay? So for example,
It's 3 pi.
yeah.
Oh.
Yeah? Okay. Okay.
Why did you do t with pi?
Okay, so sine is 0 at 0 and pi, But it's 0 and sine is 0 when the angle is equal to 0 or pi. So you have to take the angle and set it equal to 0 and pi because you ultimately have to solve for t. Okay? Okay? All right, so it's moving to the right. From 0 to pi over 3. Do you see how you can't include either of them here? All right? And it's moving to the left from pi over 3 to pi over 2.
Why can't you include?
Because both of those are where the velocity equals 0. So it's not moving anywhere. It's just not moving at all. Okay, B. Determine the particle's displacement and the final position. So B. Displacement is 0 to pi over 2, 6 sine 3t dt. Okay, so you should be able to do this by hand. So for example, this is 6. Okay, so what's the integral of sine? It's negative cosine, right? So negative 6 cosine 3t, and then if you do the u substitution, you're going to divide all this by 3. Okay? From 0 to pi over 2. And then when you plug all this in, you get 2 meters is the displacement. Okay. What is a particle's final position? Well, s of 0 is equal to 3. So the final position, s of pi over 2, let's get used to writing in that notation, is equal to s of 0 plus the integral. You should show this step. Sine 3t dt. So this is equal to 3 plus 2, 5 meters. Okay?
But we don't need to write like it's moving. I don't know. On the last problem we wrote particles 90 meters to the right of where.
I just wrote that to just explain it to you guys. You don't necessarily, yeah. Okay. So here, from 0 to pi over 2 for the total distance, we want the absolute value of this. And that's 6 meters. Okay, yeah. So initial velocity of 5 miles an hour. And we're told that v of 0 is 5. Accelerates at a rate of 2.4 t miles per hour for 8 seconds. Okay? How fast is the car going when the 8 seconds are up? So, initial velocity is 5 meters per hour. So when the problem starts, this thing is already moving at 5 miles per hour. Okay? But it's also accelerating 2.4 t miles per hour per second for 8 seconds. So like every second the velocity is increasing more. So it increased 8 times, let's say. Okay? And we want to know how fast is it going now after the 8 seconds. So here's how we're going to do this. V of 8 is equal to how much the velocity was at the very beginning plus the total amount that it changed in the 8 seconds. Okay? All right? Now, let's think about this for a minute because there's like a whole bunch of units going on here. Okay? The acceleration is in miles per hour, but then we've got 8 seconds. So this is all happening in 8 seconds. So you want to make sure that your units are consistent. Okay, so This bit, the acceleration is in miles per hour. Yeah? I'm sorry, is it in miles per hour? It's in miles per hour per second. All right? Because it's acceleration. Now, you're adding this from 0 to 8 seconds. So this dt, the 0 and the 8 and the dt go together. They have the same units. So it's times 8 seconds, basically. That's in seconds. So that goes away, meaning you're left with miles per hour. And that's important to know because the v of 0 is also in miles per hour. So you want to make sure that you're adding consistent units. Okay, now, v of 8 is equal to, the initial velocity is 5 plus, this one is 76.8. So v of 8 is equal to 81.8 miles per hour. I prefer that notation to the other notation. Huh? Okay, now B. How far did the car travel during those 8 seconds? Okay, how far did it travel? Okay, so what we need is total distance then. And that's equal to, what is the total distance? It's the integral of v of t dt, but absolute value of v of t dt. Okay?
Oh, that's how it's different. That's the whole point.
Yeah.
Value. So when you minus it, it could still be
Right.
Mm-hmm.
But now, I don't have an expression for v of t, guys. What am I going to do?
Cry.
No, we're going to take the integral v of t is equal to the integral of a of t dt. I need an expression for this. So, v of t is equal to the integral 2.4 t dt. When I take the integral of this, I get 1.2 t squared plus c. Now I need an initial condition. If only I had an initial condition. Oh my God, I do have an initial condition. I'm told v of 0 is equal to 5. Okay? So when t is 0, velocity is 5. Meaning 5 is equal to 1.2 times 0 plus c. So c is 5. That means, what's v of t? 1.2 t squared plus 5. Okay? So I did it, I didn't have a v of t, but I made one for myself. So now I can find the total distance because that's equal to the integral from 0 to 8, 1.2 t squared plus 5 in the integral dt.
Oh, we did find it, yeah.
Huh?
We did find it, yeah. I thought
we found Yeah.
it.
How do you calculate the
Use your calculator. Okay, now, let's talk about units again. This is in miles per hour, right? Yes. The 0 times the 8 is in what? Seconds. But if I need, sorry. So let me write it like this. This is miles per hour times seconds. I need to end in what units? Miles, right? So I need to multiply. So for this, I get 244, but I need to divide it by 3,600 in order to get the correct miles of 0.068 miles. Okay? So I need this dt to have been in hours as well. So I need to divide by 3,600 in order to make it into hours. Okay. All right. So.
Which was the 244 again? Was That one happened.
from the integral.
That integral, right?
Yeah. Okay, one more. The figure in the equation below give the velocity of a particle moving along a horizontal s-axis for 0 to 5. Describe the motion of the particle. So ds dt is equal to this. Okay, so when it says describe the motion of the particle, you want to talk about when is it going to the left, when is it going to the right, when has it stopped, okay? We're not talking about, oh, it was a wonderful journey. That's not how we're talking about, describing the motion. Okay, so what do we have here? We have v of t, right? And we want to talk about the motion of the particle. So, you have to figure out here where the velocity was equal to 0. And you want to do this using your calculator. So you want to use your calculator to find zeros. And what you want to find the zeros of is this. You want to set v of t is equal to t squared minus 8 over t plus 1 squared equal to 0. Okay? And as it turns out, this is 0 at t equal to 1.254. Okay, this is when velocity is equal to 0. Okay, before that, velocity is negative, so it's moving to the left. All right, so we say it's moving to the left from 0 to 1.254. It's moving to the right from 1.254 to 5. Right? That's what my domain is. And then it is stopped at t equals 1.254. Okay? Okay, now, suppose the initial position of the particle in this example is this. What is the particle's position at t equals 1 and t equals 5 seconds? Okay, to do this, remember way back when I wrote like a little chart for us saying like, v is a prime and a is v double prime and whatever. Let's do that, but with integrals now. This, you need to have like straight. A of t dt is equal to v of t plus c. You should always have that like written down somewhere, like not as a cheat sheet, but just, just written down in the back of your mind. And then integral v of t dt is what? Yep, s of t plus c. Okay, this is like the law of the land for this unit. Okay? All right.
Wait, is that the A of T?
Yep. Okay, now, so suppose the initial position is s of 0 equals this. What is the particle's position? All right, so we want position. We want s of t. That means we have to integrate v of t. Do we have v of t? Do we? No, this is from example 4. We have v of t here, right? In example 4, right here. This is v of t. Yeah.
Sorry, for the answer you just got the v of t plus c and s of t plus c. How do we know that the c's would be the same? That they're the same?
Wait, here?
Yeah.
No, this isn't answers. I'm just writing how you get one from the other. Yeah. Okay, so we want s of t. S of t is, so the final position, right, is where it was at s of 0 plus, so we want the position at, I'm sorry, I didn't mean to write s of t. We want the position at 1, which is s of 1. That's s of 0 plus how much it changed from 0 to 1, and that's the velocity. Oh my gosh. Okay, so look, I'm going to write it like this to be able to integrate. Okay? So final position is the initial position plus how much the position changed, dt. We're going to do this without a calculator. All right, so this is what I'm using. New position is initial position plus displacement. So this is s of 0 plus, when you integrate this, you get t cubed over 3. And then here we get plus 8 over t plus 1, right? Because it's t plus 1 to the minus 1 from 0 to 1. So this is 9 plus 1 over 3 plus 8 over 2 minus 8 when you plug in the 0. So this is 16 over 3. Okay. Now, B, I want S of 5. So it's the same sort of deal. S of 5. Because this is when I plugged in the 1.
Yeah.
Minus, you plug in the 0, you get 0 plus 8 over 1, which is 8.
Oh.
Okay? So now, S of 5 is S of 0 plus the same thing, 0 to 5, t squared minus 8, t plus 1 to the negative 2 dt. You have to write that step again, okay? So this is S of 0 plus t cubed over 3 plus 8 over t plus 1. This time we're going from 0 to 5.
So you have to rewrite that first step.
Yeah. Yep. 9 plus, so that's 5 cubed over 3 plus 8 over 6. What's 8 over 6 these days? 4/3 minus 8 again. Okay? So look, that's 9 minus 8, that's 1. And then what's 5 cubed nowadays? 125 plus 4. That's 129 over 3. And that's divisible by 3, believe it or not. What's 129 divided by 3?
43.
Oh, 43. So that's 44. Look at that. Yay. Okay? All right.
Let's say 5 cubed though.
Yeah. And I think we'll stop here.